Like we discussed yesterday, we are still considering the exact area between a curve and an axis. We're going to be looking at it this time through anti-differentiation, which we got a very light taste of previously. Now, the exact area matters a lot because, well, you know why. We've looked at a few situations where it matters. Won't belabor the issue. So, quick reminder of what we talked about yesterday. We talked about how an antiderivative can be thought of quite a few different ways. One of those ways would be to say that an antiderivative is coming up with the function whose derivative is pictured. Another way you could think about an antiderivative, you could think about how you're doing the differentiation process in reverse. Those would be two, I think, profitable ways to think about what an antiderivative is. And please recognize that this is brand new mathematics to you. And when you do brand new mathematics of sufficient difficulty, it's going to take a little while just to get used to it. So having these different ideas about antiderivatives is going to be important because that's how we actually answer questions. So we looked at a single problem yesterday, specifically 2x minus 2, and I gave you 6 sample answers and said we actually don't have a single final answer. That's why we use this plus C business, because any of these constants, if we take the derivative, results in 0. And quite frankly, we don't know which one of those constants to take. So that's what the plus C does. Now I asked you to hopefully be perplexed by a couple of things from the end of class yesterday. So I was trying to leave you with a couple of things just to think about, because a lot of times in math, all of the mystery has been taken away. All the wondering is gone. None of the thinking is present. You just like follow along and you memorize. And that's actually why you get into trouble in calculus, because being passive like that in calculus leads you to have lots of problems, because there's one thing calculus is not, it is passive. It is very active. So I gave you a single hint, and the single hint about why 3/4 v to the 4/3 power plus c is the correct function whose derivative is the cubed root of v, that single hint was v to the 1/3 power. So this was one of the things that I hope was perplexing to you. You were thinking a lot about why is the correct answer here 3/4 v to the 4/3 power plus c. So the answer to that can be very unhelpful and very brief, and it is take the derivative of 3/4 v to the 4/3 power plus c. What do you get? Do you get v to the 1/3 power? The answer is yes. How come? Well, we have 3/4 times the derivative of v to the 4/3 power, and we learned when we take the derivative of v to the 4/3 power, we subtract 1 from the exponent, and subtracting 1 from 4/3 makes 1/3, because 1 is 3/3. The derivative of c is 0. If you do 4/3 times 3/4, you get 1. You get v to the 1/3 power, which is the same thing as the cube root of v. So what's going on here? Well, we don't want to try to do anti-differentiation with guess and check. We want to do anti-differentiation methodically. You are, I mean, once you get experience, you'll be probably decent at guess and check, but there's going to always be those situations. You know they happen. You've done calculus long enough. There's going to be those situations where guess and check doesn't work. So what do? Well, you need some type of a method. So what we're talking about here, or the pattern we could be thinking about what makes this work and the previous one work, is I have a 1/3 power. I know that I took a derivative to get to a 1/3 power, right? So that means I subtracted 1 from some number. So I think backwards and I say, okay, 1/3 add 1 to that, because that's the opposite of subtracting 1, because again, I'm doing an antiderivative, which means I'm doing a reverse derivative. So if I add 1 to 1/3, I get 4/3. Okay, so that part makes sense. It's like, I got that, all right? So v to the 4/3 power, I know I want that because when I take the derivative of v to the 4/3 power, I'm gonna have v to the 1/3 power. Make sense? I hope so. But remember what happens when you take the derivative of v to the 4/3 power, you have 4/3 times v to the 1/3 plus 0, of course, from the c. And if you compare 4/3 v to the 1/3 to the problem we started with, those don't match. That 4/3 right there needs to be a 1. So how do you get it to be a 1? You multiply by 3/4. I think 3/4 times 4/3 is 1, or the reciprocal of the new exponent. So I hope that that answers for you one of the things that was perplexing yesterday when I revealed this to you and asked you to just think about it for a while. We're going to next look at the other thing that I hope you thought about and wondered about. I didn't explicitly state this one, but that one is, how come the notation for antidifferentiation looks so much like the notation for doing a definite integral for finding area? Why are those like the same, pretty much? You might have wondered that, okay? Maybe you did, maybe you didn't. Hopefully you are now. I'm gonna pause the recording here, see if there's any questions. Why is the notation the same? Because the math here is the same. Yeah, that's why. Super helpful answer, right? Well, here's why. Check out this, the fundamental theorem of calculus that we looked at previously. We looked at one aspect of the fundamental theorem of calculus earlier today, wherein we took the derivative of an integrally defined function. It was g of x equals the definite integral from -1 to x of f of t dt, and we said g prime of x was f of x. So that's one aspect of the fundamental theorem of calculus, which tells us if you take the derivative of an integrally defined function, you get the integrand as the derivative. Here's the other aspect of the fundamental theorem of calculus, which we have yet to review, but we are reviewing now. So if we have a function f of x, which is continuous on the closed interval ab, and capital F of x is an antiderivative of f of x, quick pause. Capital F of x is an antiderivative. That means capital F of x, if I take the derivative of it, is the same function as lowercase f of x, which is the integrand, the inside function part, the height part, if you will, of the area. So the definite integral from a to b of f of x dx equals capital F of b minus capital F of a. So that is the fundamental theorem of calculus. The other part that we have not studied quite yet, we're about to use it to hopefully connect in a way that makes sense to you the notation of antidifferentiation and integration, and then it'll maybe make sense about why they are the same notation. Okay, so let me get this set up here. I gotta erase some junk. So make yourself a little bit of room and write down that thing we've written down before, namely that we've got an antiderivative of 2x minus 2 dx equals x squared minus 2x plus c. Okay. So what we're going to do is change the problem slightly. We're going to change this problem from an indefinite integral or an antiderivative into a definite integral. We're going to go from -1 to 2. Yeah, that sounds right. Sure, -1 to 2, why not? Okay. So this is the problem we're actually going to consider right here. We would like the definite integral, which is the area. Okay, so we've studied this already. We know that one way we can find these areas is if we look at the graph, and the graph is something that's nice and geometric. So this line has a slope of 2 and a y-intercept of 0, -2. So down 2, left 1, perfection. Up 2, right 1. Up 2, right 1. Oh, I should not have gone to 4. I believe I need to go to, it doesn't matter. That's good enough. We'll keep it. I'll just have to change some things later on. So that is the line, yes? Yes, that is the line. So what is the area? The area is from the x value -1 to the x value 2. How do I know they're x values? Because it says dx in the integral. So I'm like that. And then the area has the function as a height. So it's 2 triangles, isn't it? Yes, 2 triangles. If I calculate the area of those 2 triangles, I'm going to have the area from -1 to 2. Okay, so let's look at the first triangle. The first triangle is going to have an area 1/2 base times height. The base goes from -1 to +1. Yep, -1 to +1. So that's 2 units. The height, now remember, this is where we need to be careful. The height doesn't mean height of a triangle. The height of this triangle is 4 units, but the height of the function value, that's what height means here. The function value is -4. So the area of that first triangle is -4. Okay. The second triangle, this second triangle goes from 1 to 2. I believe that is a base of 1. Yes, base of 1. Okay. And then the height of the triangle is 2 units, which is also f, or we didn't name the function f, but pretend the function is named f of 2. Okay, so that gives us a value of 1. Which means altogether, this integral has a value of -3. Okay, hopefully that makes sense to you based on what we've been doing. We are going to use the fundamental theorem of calculus here now to determine the exact same result. Math is amazing. Oh, I gotta change that. We're not doing 4. We're doing 2. All right. So the definite integral from -2 to 2 of 2x minus 2 with respect to x. That's what we're talking about here. We're going to do the exact same problem. We're going to do it differently. We're going to get the same answer. Hard to believe, I know, but it'll work, I think. Let's find out. So the fundamental theorem of calculus says that this definite integral equals an antiderivative of 2x minus 2 -1. Sorry about that. We definitely won't be getting the same value with the limit integration. All right, they're not the same shape anyway, as per usual. So this is what we want to do. We want to take that antiderivative that we looked at before, and according to the fundamental theorem of calculus, if we evaluate this at 2, evaluate this at -1, then subtract them, we're going to figure out what the area is. So our answer here had better be -3, right? Okay, let's see if we set this up correctly. So evaluating An antiderivative of 2x minus 2 at 2 gives 2 times 2 is, 2 squared is 4. 2 times 2 is 4, so that's 4 minus 4 plus c. Right, check my arithmetic. 2 squared is 4, 2 times 2 is 4, 4 minus 4 plus c, okay? Then I've got to do this at -1, so I do -1 squared, that's +1. -2 times -1 is +1. Plus c. Okay, that's not correct there, Mr. Genius. Plus 2 would be correct. Sorry about that. I'm falling apart. And then I subtract those. Again, we're doing the fundamental theorem of calculus. It says, evaluate an antiderivative of 2x minus 2 at 2. Did that here. 4 minus 4 plus c. At -1, did that here in green. 1 plus 2 plus c. Then subtract those values. Okay? So what do we get? We get 4 minus 4 is 0, plus c is c. 1 plus 2 is 3. So I have c minus 3 minus c, which is -3. How do you like them apples? 'Tis the same. So the notation for antidifferentiation and integration are the same because they do the same math. So you may be wondering to yourself, okay, why would I need to do this? I already have a method that works. I could draw a graph. I could find the area of the triangles. I could be good to go, right? Yeah, okay. Well, check out this next one that we're not going to do all the way. It's the definite integral from -1 to 2 of x squared plus 4. Okay. So if we look at this graph, it's a parabola that opens up, has a vertex at 0, 4. If we do this thing from -1 to 2, that is the shape we would be finding. That shape right there is not a geometric shape, so I can't just be like, oh, find the area of the triangle, find the area of the other triangle, add them together. I have to, for this non-geometric shape, use the fundamental theorem of calculus. And if I use the fundamental theorem of calculus, find an antiderivative of x squared plus 4, evaluate at 2, evaluate at -1, subtract them, I'm going to get to the area. This works 100 times out of 100. This always works. This is another good time to pause the recording here. So if you've got questions you've been saving up, this would be a great opportunity to ask them. So the fundamental theorem of calculus is rather valuable. It allows us to find these areas without being restricted to geometric areas. High five, fundamental theorem of calculus, you're the best. But this antiderivative stuff is not as nice as it could be. So we talked about this earlier. If you did not write this down, here's your chance to write this down. We have many techniques to find antiderivatives, many techniques. We won't even study all of the techniques in this class. We will study a lot. We will definitely study a lot. We won't study all of them. Honestly, some of them are quite silly to use. They're exceedingly complicated for not much benefit, especially in an age of technology, but more on that in the future. So one of the antiderivative techniques that we are studying is this one. So we looked at this briefly when we talked about v to the 1/3 power, the cube root of v. So there is a power function antiderivative technique. A power function antiderivative technique. And the way it works is you take your power function derivative shortcut or technique and you do it backwards. So what do? To go backwards, you add 1 to the original exponent. Please notice this asterisk. That is a very important asterisk for the power function anti-differentiation technique. Then you multiply by the reciprocal of whatever your new exponent is. So what happens? That's what you may be wondering. Well, let's look at the antiderivative of 2x squared to get an idea of what's going on. All right, so this will be a little bit quick here. So one thing I would like to remind you of is we can factor out that 2. That is one of those properties of integrals we looked at. And what we're considering is the antiderivative of just x squared. So we notice that x squared is a power function. And as it is a power function, we should employ the x squared technique. I'm sorry, the power function technique on x squared. So how do we do that? Well, we've identified this as a power function. We should add 1 to the original exponent. So this is going to be 2 times, what is I can't do 2 plus 1 yet. I'm just going to write it down as 2 plus 1. And then I need to multiply by the reciprocal of 2 plus 1. Oh, 2 plus 1 is 3. And then remember, this is an indefinite integral. We don't know what the constant is. We need to remind ourselves that such a constant exists. That's what the plus c does. So if we simplify, 2 times 1/3 is 2/3. 2 plus 1 is 3. So antiderivative 2x squared with respect to x is 2/3 x cubed plus c. Here is one of the beautiful things about antiderivatives right here. You can always check your work for your antiderivative. So you pretend this is not an antiderivative. You just pretend this is a function you wish to take the derivative of. So how would you take the derivative of 2/3 x cubed? You'd say 2/3 times the derivative of x cubed, which is 3x squared, plus the derivative of c. Remember, c is a constant, and that is 0. And then you simplify. 2/3 times 3 is 6/3, which is 2x squared, plus 0 is 2x squared. And then I compare 2x squared to my original. Is 2x squared the same thing as 2x squared? Yes. Yes, it is. Therefore, I have performed the power function anti-differentiation technique correctly. Are you ready for the asterisk? You had better be, because that's what we're looking at next. There is a singular exception to the power function technique for anti-differentiation, and that is the power of -1. If you have a power of -1, you do not have an antiderivative that is a power function. This is the only exception. If you have an exponent of -1 for your power, you do not have a power function. You will not follow the power function shortcut. You won't add 1 and multiply by the reciprocal. Think about that for 2 seconds. Exponent -1, add 1, multiply by the reciprocal. Yep. Sounds bad. This is the shortcut. This is the technique. This is the thing that we will do if we are presented with the power function x cubed. We will say that an antiderivative of x to the -1st power with respect to x, the dx, equals natural log of the absolute value of x plus c. Now you're wondering right now where the absolute value comes in, and there are reasons why we do the absolute value. Reasons I will not be getting into today, reasons I actually won't be getting into for a little while. If you really must know, please ask me outside of class. I'd be happy to explain them to you. Now, here's what I need you to do. I need you to all to pause whatever it is you're doing. I'm going to drop some Galaxy Brain. Okay, you ready? Galaxy Brain time. You know how you've studied math before calculus? Algebra 1, geometry, algebra. Some of you are not pausing for the Galaxy Brain. You know I can see you, right? Okay. So Galaxy Brain moment. You know how you've done that? Algebra 1, Algebra 2, pre-calculus, geometry, all that stuff? You know how you did all those weird like symbols and crap and you moved things around and you did this and this, that, and you're like, wow, I did this problem. Cool, I'm done. The vast majority of those manipulation skills that you studied, trig identities, exponent properties, logarithms, natural logarithms, all that stuff, the vast majority of it has to do with taking an integrand and manipulating it so that you have a function that fits your anti-differentiation techniques. All right, you can go back to writing. So you spent all of these years essentially preparing for this. We're going to take all of those skills of manipulation. We're going to use just about every last one of them, and we're going to take a lot of integrands, so a lot of functions, and we're going to manipulate them in such a way. This is the limitation of anti-differentiation. Anti-differentiation has some real bad. We'll get to that later. But for right now, make sure you have some idea of the two techniques we've studied. We've studied the power function anti-differentiation technique, add 1, multiply by reciprocal. We've studied the power function exception, negative first power, or 1 over x. That's natural log of the absolute value of x plus c. There are a bunch of other antiderivative techniques we're going to look at now. Here is the first batch. There are two functions in the first batch. One of them is e to the x. An antiderivative e to the x with respect to x is e to the x plus c. How come? Well, the derivative of e to the x is e to the x, right? Right. Plus c because we don't know the constant. So you may be thinking to yourself, okay, e to the x is e to the x. How about natural log of x? Well, we need to wait on further techniques to get an antiderivative for natural log of x. Okay, so that one will be coming later. We don't have what we need yet, and we won't until later next week. So what else could we talk about? We could talk about trig. We talked about a lot of trig, right? Think about all of your trig and inverse trig antiderivative shortcuts. There's a bunch of them, right? Right. So here's the first one we're going to talk about. I'm going to make it multiple choice. Antiderivative sine of x dx, is that cosine of x plus c or is that negative cosine of x plus c? Which one ought you to memorize as an antiderivative for sine of x? So which one is the correct technique? Cosine of x plus c, negative cosine of x plus c. You should think about it. Calculus is active, of course. So which one is it? Well, let's find out. Take the derivative of cosine of x. What is it? Derivative of cosine of x is negative sine of x. What's the derivative of c? 0. Is negative sine of x the same thing as sine of x? How about that? Are those the same? No, those are not the same. That is how I know this negative cosine of x plus c is the correct antiderivative technique I need to learn for sine of x. Let's look at a few more. You might be thinking to yourself, tangent of x. That would be a good one to do after talking about sine of x, right? Tangent of x. Tangent of x, we're going to have to wait. We are going to have to wait on tangent of x. Sorry, we're not going to have that one for a little while. We'll have that one next week, but not yet. Okay. So what else are you thinking about? You may be thinking about cosine. We can do cosine. Cosine of x is sine of x plus c. How come? Well, an antiderivative is the function whose derivative is given. The derivative of sine of x is cosine of x. The derivative of c is 0. 0 plus cosine of x is cosine of x. Here's another one. Antiderivative secant squared of x dx. That is tangent of x plus c. Another antiderivative technique that works because the derivative of tangent is secant squared. So you may be thinking to yourself, okay, secant squared, how about regular secant? Regular secant is going to have to wait. Sorry, guys. That one's going to have to wait. We need more math for that. Okay, what about cosecant squared of x dx? Yep, we can do that one. That one is the opposite of cotangent of x plus c. How come? Take the derivative of cotangent of x. You get the opposite of cosecant squared of x. That's why there's an opposite here. Okay, how about a few more? Yes, let's have a few more. Here you go. Here is a few more. Make sure you have all those written down. I'm going to pause the recording here. So that's a bunch more. Some of these we have to wait on again. Inverse tangent, cosecant, cotangent. We don't have the skills. We won't have those skills for a little while. Everything I've shown you so far, I hope you recognize as a derivative shortcut we memorized, but backwards. That's what these basic antiderivative techniques are. So pay no attention to this. We need to talk about the bad news, which you've already gotten a taste of for antiderivatives. So here's the bad news about antiderivatives. There's four things. First thing is there is no universal product rule. What I mean by that is if you have a product of two functions that you are trying to find an antiderivative of, there is no single technique, no universal rule, no one thing that always does products. In derivative land, there is. In antiderivative land, there is not. There are many. Similarly, for the quotient rule, in differentiation, there was a thing, a procedure that you could follow, a rule, a pattern that worked 100 times out of 100 if executed correctly to find the derivative of a function presented as a quotient. There are no such singular paths when it comes to antidifferentiation. There are many paths. So we need to shift our thinking. The third piece of bad news, there is no, pour one out here, sad face, no mother of all antiderivative rules. Yeah, there's no chain rule. There's no chain rule antiderivative. Can't do it. There are many techniques that allow us to, in certain situations, go backwards on the chain rule. And here's the one that may make some of you sad. I'm rather indifferent to it because I'm okay with this in my life. You may not be. Friends, neighbors, countrymen, lend me your ears. There are functions that do not have an antiderivative function. There are functions that exist for which you can never, ever, ever, not using any technique, not using guess and check, not using anything, that is an antiderivative of certain functions. We will learn what to do in those cases. But these are the four really pieces of really bad news for antidifferentiation. And this is why antidifferentiation is much more complicated in total, I think, than differentiation. So get over your grief real fast. We're going to do some practice. And by some practice, I mean two things. So we are going to look at an antiderivative of 2 plus sine of x with respect to x. That's what we're going to look at first. Antiderivative of 2 plus sine of x with respect to x. And the way we're going to look at this is I'm going to try to break it down for you into 3 pieces to hopefully make it comprehensible. Okay, so we got that written down, yes? All right, here are the 3 things we're going to do this. So notice how I've written down the second thing and the third thing? You, of course, are wondering what is the first thing. The first thing that you should always do anytime you're doing an indefinite integral, an antiderivative, anything, is always think about how there is a constant c. We don't know what the constant c is, and in this problem especially, we don't have any information to figure out what c is, but we must always consider that. Make sure you always consider that. The other things that we're going to do is we're going to consider separately, because this is a property of integration we've talked about, 2 dx and sine of x dx. And I'm going to try to convince you that antiderivative of 2 is 2x and antiderivative of sine of x is negative cosine of x. So how am I going to do that? Well, I'm going to try to model for you what you want to be thinking about. So when you see a function 2, what you want to be thinking to yourself is, which one of my antiderivative techniques, which I'm slowly memorizing, works here? Is it an inverse trig one? Definitely not. Is it sine? Definitely not. Okay, what is it? Would you believe it's a power function? It is a power function. Let me convince you that it's a power function. It is a power function because 2 is 2x to the 0 power. If you think about this as 2x to the 0 power, that's a power function of the power 0. It's not a power function of the power -1, so it's not a natural log. So I add 1 to 0, and I multiply by the reciprocal. Looks like this. So it's 2 times x to the 0, 0 plus 1 is 1. Reciprocal of 1 is 1. So 2x. You can always check this, of course, by differentiating 2x. Hey, what's the derivative of 2x? Is it 2? It's 2. Nailed it. Sorry, went way too far. Okay. How about convincing you that antiderivative of sine of x is negative cosine of x? How could I do that? I'd look at my trig list, right? It's on the trig list, isn't it? Isn't sine of x on the trig list? Sine of x is on the trig list. Also, we can always convince ourselves that this is the case by taking the derivative of negative cosine of x. If you take the derivative of negative cosine of x with respect to x, you have -1 times the derivative of cosine of x. The derivative of cosine of x is negative sine of x. -1 times -1 is positive sine of x. So c plus 2x minus cosine of x. Now, generally, I'll tell you that the c is written last. So I will do that here. But honestly, it doesn't matter. It's just addition and subtraction. Order does not matter. Just as long as the signs are preserved, positive c, positive 2x, negative cosine of x, everything's fine. So let us speak of the next one. This one's going to go a little bit faster. Okay, so give that a nice look. That is antiderivative of 3 divided by x plus secant of x tangent of x minus e to the x dx. Or, read more helpfully as, find the function whose derivative is 3 divided by x plus secant of x times tangent of x minus e to the x. That's another way you could read this. And I'm going to do this by doing 4 things. Are you ready? I hope so. What is the first thing? The first thing is, of course, as this is an indefinite integral, I'm going to consider how I don't know what the constant is. I call it capital C. The second thing I'm going to do is I'm going to look at just the first term, 3 divided by x. And I'm going to think to myself, okay, 3 divided by x, of the antiderivative techniques that I possess, that I know, which of them makes sense here? Okay. If I don't know, often it will be fruitful, helpful, useful to write what I have in several different ways until I have something in a way that helps me. This is going to be what frustrates some of you, is you don't get it right the first time. Well, if you don't get it right the first time, hopefully you've learned in calculus. That means that you should try a second time. So this is, of course it is 3 times the natural log of the absolute value of x. That is a power function that's not a power function, right? Yes, I knew that because I had an exponent of -1. Okay. So let's talk about the third thing. The third thing is looking at, ooh, this is just a disaster of organization, excuse me. Let's talk about secant of x, tangent of x. All right. Definitely a trig function, right? Is it a trig function that's on the list? It absolutely is. This is on the trig list. So on the trig list of antiderivative techniques, I know that this is going to equal secant of x because the derivative of secant of x is secant of x tangent of x, right? Right. So my third thing comes from using the trig list. That's secant of x. Oh, forgive the color switch there. Okay, last one. We've got antiderivative of e to the x. So how are we going to do antiderivative of e to the x? Well, we're going to think about all of our anti-differentiation techniques. If you want to do it by process of elimination, that's fine too. You could say, well, it's not a trig function. It's not natural log. It's not a power function. Oh, it's the e to the x one. E to the x is e to the x. That then is the final answer. Pretty nifty. So you got some practice on WebAssign. That will have lots of chances for you to do this. That is concentrated on Friday.